Welcome again to the NPTEL course on storage systems. In the previous classes, we were looking at issues relating to the design of the Google file system, and we also looked at some of the problems in that system and how a newer system called the Big Table handle some of these issues. Okay. So, just as a summary, if you look at what we discussed previously, the Big Table has three main components: a library that is linked into every client, a master server, and many tablet servers. The tablet servers basically have multiple rows, and that is a unit of distribution. And again, if tablet servers, they can fail, or you can if you have more rows coming in, you want to move it to a new machine, that also can come in. So, to accommodate changes in workloads, this kind of dynamic activities with respect to tablet servers keep happening. Again, you have a master which actually does assigning of tablets to tablet servers, detecting which tablet servers are available, which are no longer working. You need to do some balancing, and then you also need to do some garbage collection of files in the GFS. Basically, it turns out that the GFS and Big Table together work similar to what is called a log structured file system. You keep some information, and then some older information becomes stale, which has to be deleted. And so, that garbage collection is an important part of the system, and the Big Table actually manages the garbage collection of files in GFS. As you remember, there is no, when you do delete in GFS, it is just marked as deleted, it does not do something immediately. Okay. It is done later as part of this garbage collection service. Okay. Now, it also handles certain other things like if you change the schema. So, I think we will just briefly look at the interaction between GFS and Big Table one more time. The important thing to remember is that the persistent state of a tablet is stored in GFS. Okay. So, basically when writes come in, you commit to a commit log, and these ones which get committed are sorted and buffered in memory, and those sorted and buffered records are called as mem tables. So, all this stuff is in memory. And then just like in log structured file systems, once you are running out of space, for example, memory for example, you can push out those full mem tables, reasonably full mem tables, onto persistent storage, the SST tables, and this is what is being stored in GFS. Okay. So, in case there are any reads coming in, the information can be in multiple places. It can be mem tables because that is where recently it got put in, or it could be in older ones. And because it acts like a, let us say, it does not really delete old information immediately, stale information also can be there. You need to figure out which is the most recent one, and of all the possible mem tables and SS tables, you have to find the most current one. So, in a sense, you have to look up all these tables. Now, because these things are sorted, you can do this fairly easily, because notice that all these tables are sorted, otherwise you are going to have a very hard time finding out in each of these tables. So, because they are sorted, it is easy to check each one of these things and figure out which is the most recent version that I am interested in and pick it up. This is somewhat different from a log structured file system, where you need to have additional indexing information by which you can actually check up and look up what you really need. Okay. So, there is a slight difference between the way this is done here and there. Here the sorting actually helps it to be much more, it is certainly time consuming, but it is easier when it comes for looking up reads. Okay. Again, if there are any failures, the persistent state is sitting in the GFS. Basically, I have to read the tablet, and then basically the tablet server has to read its metadata, which is basically a set of those updates stored in SS tables, basically the ones which have been made persistent. You have to read all those things into memory, and you also have a set of redo points. Basically, these are the points where basically the commit logs tell you that this contains data for the tablet. Okay. So, and these data read into memory, and you have to basically reconstruct the mem table, because I told you the mem table is the thing which keeps the current set of recently committed ones. Okay. And then you can continue from here. Okay. So, this is how the system has been set up. There is an interaction between GFS and Big Table. GFS actually worries mostly about things like how to store it efficiently in 64 megabyte chunks, for example, and it also worries about reliability. It worries about how updates are done. It tries to do something about how to ensure that atomic appends take place. So, those are the kind of stuff that GFS worries about. Big Table, on the other hand, tries to be more closer to the application, and it tries to figure out how to make record structures available to the application. Okay. And so, you buffer multiple records as things are coming in some kind of a log structured manner, and keep pushing it out to GFS once you have certain amount of size. Okay. So, this is how the interaction, that's how the GFS and Big Table have been designed. It's an example of what you might call as a cross-layer design. Okay. Each party tries to do certain things, but you try to ensure that the right set of functionalities are the different layers. Okay. So, that is the idea, and GFS came first, and it was designed for handling mostly web search and crawling of data. And the Big Table came in because a lot of people are doing other things also with it, and you need an easier way to interact with this GFS system. So, it is slightly closer to application level design. So, now we will take a look at slightly similar systems that have been designed. Hadoop is one which is closely modeled on the GFS/Big Table kind of model, and they say it is a rack-aware file system. Actually, most of the systems that we talk about are actually rack-aware, or sometimes even what I call data center aware. They exactly know whether, let us say, if a data is present, they know which rack it is present in, so that if you want to replicate it, they might want to keep it on a different rack. Or it can also be, if you want to do geographic distribution, they also ensure that it can be replicated in places which are quite far away from the one of the data centers we are talking about. So, the same data can be in multiple data centers which are distributed located. Okay. And this is an important issue because the latency and bandwidth aspects are closely correlated with whether it is within a rack or across racks within a data center or geographically distributed. Okay. So, essentially all these file systems are that, but Hadoop also makes explicitly the claim that it's a rack-aware file system, just like also I think Cassandra and other kinds of systems also. Okay. And basically the idea is to make sure that the work whatever is being done is actually closer to where the data is there. If it is not that, try to be near the rack, same rack, near switch, so that you try to reduce backbone traffic. Again, HDFS also stores large files just as GFS does, and this is also 64 megabyte chunks. Okay. Similar to GFS, they also do reliability by replicating data across multiple hosts. They don't use RAID storage on hosts, okay, because they find it expensive and not giving as much reliability as if you were to distribute across multiple nodes. Basically, even if you have RAID storage, if the machine dies, then you don't have access to the data. So that's why RAID storage is not similar to again GFS. And above that, there are all these other closer to application level entities like map reduce engines, etc. And some other entities like job tracker, which is doing the scheduling part, which is worrying about scheduling. Okay. So this is an open source system compared to GFS, and so it's being widely used, and quite a bit of recent infrastructure from other major companies also use DFS. Okay. So there are a lot of differences between this and GFS, but I just wanted to point out that there is a lot of similarity also with respect to the kind of GFS kind of design we discussed. We'll also look at briefly look at another design. Yahoo has come up with some system called Peanuts, which is a large distributed, geographically distributed data serving system for web applications. So basically, what they are trying to look for is how to support workloads, mostly of queries that read and write single records or small groups of records. So, and not for complex queries. Again, because if the workloads are mostly dealing with single records or small groups of records, then it is slightly easier to manage consistency also. Okay, because notice that GFS and other systems usually provide atomicity for only a single rows. Okay. So if it is single records or groups of records, possibly it is there in a single node, and probably it can give you a lot more guarantees than otherwise possible. Okay. The data in this particular system is organized as hashed or ordered tables. Again, we'll talk about this hashing soon. This is another different model of storing data, and we briefly looked into it some time back, but I think we'll look at it in some additional detail with respect to what is called consistent hashing. We'll look at that part of it soon. Okay. And the most important thing that they are trying to do is to design it for low latency for large numbers of concurrent requests, including updates and queries. So because of this, anything that is high latency, they usually do it asynchronously. Okay. And other thing they do is they want to support a system by which if you are modifying any records, you can actually have a master for it, so that it becomes a local operation for you when you update those things. Okay. So essentially, you can cache it and update it. In some sense, it's something like a session semantics. Okay. You copy it, keep it with you, update it as much as you want, and then put it out back. Okay. So you want to do as many local operations as far as possible. Okay. Other thing that this system does is give you per record consistency guarantees. All replicas of a given record apply all updates to the record in the same order. Okay. So we will look at this a bit more. Basically, you notice that in GFS etc. also, you'll find that the updates happen in decided by the master. Only thing is that different, let us say, when a master does one particular set of ordering of updates, if it fails, the new master can do it in different order. So there are some issues with respect to the kind of updates that are present in, if you're doing, for example, appends, right? You'll find that they can be in different orders on different machines. Okay. So what is attempted here is to give additional control to the application, so that you can say that with respect to a record, at least all replicas of a given record apply all the updates to the record in the same order. Okay. So you want to now, instead of doing it at the slightly higher levels, you want to do it at slightly record level, and similar to what is given in big table with respect to rows. Okay. For example, they have something called timeline consistency model. So, the basic idea is a particular object has a timeline. In a sense, it has got, for example, it got read here, it got modified here, etc. Okay. There are various versions of the object available. So, reads are served using a local copy, but this may be stale with respect to the more current version somewhere else. But the application API can specifically ask for a particular version or any version greater than a particular number. For example, I can say, give me the most current version, or better than, sorry, I want a version which is more than the 5th version. Okay. So, basically, while copies may lag master record, every copy goes through the same sequence of changes. So, in a sense, there is a timeline for objects at all places. Okay. So, you can essentially say the following, that I am interested in a particular version or any version later than that one. Okay. And because of this, it is essentially consistent across all the systems, across all the clients, it will all be consistent across. You also have a system which is test and set. Okay. Writes. You can essentially say what is the current version, and if it is this current version, I will allow the write to go through, otherwise I will not go. It will become no op. Okay. So, it turns out this can be used to also facilitate per record transactions. Okay. Essentially, you can roll back. You can try to write it. If it is not possible, you can roll back. Okay. So, of course, this means that you will be retrying certain operations multiple times before you may succeed. One of the difference between this system and previous systems we looked at is that they say they use what is called a guaranteed message delivery service rather than a persistent one. You notice that in the case of GFS and Big Table, we had certain logs, and the primary kept those logs, and then you had to use that for recovery, etc. Okay. Here, they are depending on a guaranteed message delivery service. So, there are various methods by which certain messages can be delivered and guaranteed that they actually were delivered, and they use this kind of systems. For example, they use something called publish subscribe message system. That is what is used. Okay. So, other thing that they have done is provide support for what you call triggers. That means that if some data changes, applications can register themselves with the system saying that if this particular change takes place, I want to be notified. Okay. And this is important for some applications that might invalidate cached copies after some time. Okay. So, for example, if you are serving ads in a system and there is a contract, it says after some period of time the contract expires. You want to actually remove all the ads corresponding to that. Or you might have a system which is trying to track certain websites. As soon as some modifications take place, I want to be notified because I want to re-index it. So, if you are looking for slightly real-time kind of models, you need to do this. Again, GFS also has proceeded in this direction. If you look at Google, they also have a service which is similar to this. They have something called Megastore, which does something similar to this. Okay. So, you want to essentially provide a trigger-like capability so that you get notified whenever things happen, and that is done by users subscribing to stream updates on a table. Okay. And this is an asynchronous publish subscribe message system. Okay. So, The good thing about this is that anybody can publish it and anybody can subscribe to it. They don't have to, each party doesn't know who the other party is. Okay. So basically what I'm trying to say is that if there is because everything goes through this particular message system, this particular message system keeps track of who the parties are, who are subscribing and who are publishing and who are subscribing. So for example, if you're trying to update something, one replica doesn't need to know the locations of other replicas. You just have to publish it, and then the system will actually make sure that the other subscribers who are looking for that updates, they can get to it. Okay. So those kind of things, in a sense what's happening is that there is a broker in between, okay, which actually trying to figure out what people are interested in, and they make sure that it happens. Okay. And because of the system, it turns out that they can also optimize it for geographically distant replicas. Okay. You can figure out what is the best way to push the updates. Okay. So this is in contrast to gossip-like protocols, which might not really be tuned for geographical distribution. Okay, they might not be really taking care of those kind of things. Okay. So this one other design. Okay. Again, we'll quickly look at another design, which is the Windows Azure model. This is a slightly different system because it is designed as a scalable cloud storage system, used both by end users as well as by like companies like Microsoft themselves. Okay. For example, they want to use the system for search, just like GFS was used by Google. They also wanted to export it out as a cloud storage system which other parties, anybody who is interested can use it. Okay. So their basic design is keep this data, for example, in the form of what I call blobs, user files, or in tables, structure storage, or queues, message delivery. Again, this queues is similar to what we saw in the case of Peanuts also. Okay. There also you have some kind of a message model, right? Guaranteed message delivery model. Same thing also is being done here. Okay, queues. Okay. Instead of depending on persistent logs. Okay. So basically, in this system, you have blobs for incoming and outgoing data. Again, this is similar to in the case of Big Table. You notice that incoming tables come into both mem tables, then stored persistently into SST tables, etc. Similarly, again, there's some kind of log structure going on there. So here, what is happening is that the blobs are being used for incoming and outgoing data, and the queues are used for basically this has got the message delivery, right? So the message delivery is the message essentially tell you the kind of workflow that has to happen. So that's why these queues are they are used for overall workflow processing corresponding to the blobs, and any intermediate data is stored in tables of blobs. Okay. So they say that just like Peanuts was using some triggers, they also provide publicly searchable content within a very short time of something being published. For example, they claim that, for example, within 15 seconds of somebody posting something in Facebook or Twitter, it will show up in their search let's say engines, for example Bing. So basically, because the only way they can do it is by having some way in which somebody is pushing the updates to them also. So they can subscribe to certain APIs which Facebook or Twitter is making available, so that as soon as anybody posts something, they get the data and they actually push it through their system, the cloud storage, the system out here, and then that is made available to the Bing search system, again it will re-index it so that the new results will actually can pick it up. Okay. So this is another thing that they are talking about. This Windows Azure system says that they provide strong consistency, but if you look at it closely, it's basically the same as what other people are providing. For example, if you look at what Peanuts gives you or GFS gives you, the Big Table gives you, it is basically within a tablet or within basically a data center or a rack, for example, those kind of things. Okay. And the name which Windows Azure gives is stamp. Stamp is basically one thing which is all available in a single place. It's not essentially multiple racks. Okay. They might have, for example, a stamp might have something like about few tens of terabytes of data in one single place. Okay. So they provide strong consistency within a stamp, and across they usually don't provide it, and they say that most of the times if you do intelligent partitioning, it turns out, and the upper level protocols are properly set up, almost all the things updates actually happen within a whatever you're concerned about happens actually within a stamp, so that essentially you can say that you can get strong consistency. Okay. Okay, that is the claim they make. Okay. Again, just like the previous system, if you are looking for within a stamp, within a, let us say, data center or within multiple racks, right, they usually do synchronous application, and across stamps they do asynchronous application. Okay. Again, as we know, the asynchronous thing is a thing that comes into picture anytime you have the CAP theorem in the picture, right. So as long as you are doing synchronous application, then there is no serious issue. Okay. That's why they say that they provide strong consistency. And because it's a cloud storage system, they also provide user accessible global and scalable namespace and storage. Because this is in contrast to other systems which don't have a user set of users also using the system. Okay. So they have to provide a global and scalable namespace. So I'm not going into too much detail. That actually each of the systems is quite complex, and there is considerable amount of description that's available. For example, if you want to look up Windows Azure, in the recent SOSP 2011, they have described it in some detail, and you should look up those details if you want further details. Now, if you look at the previous systems, we talked about GFS and Peanuts, etc. They basically have the model of one particular system, like the master, for example, which actually keeps track of where the actual tablets are, or the various let's say 64 megabyte chunks are, etc. They they actually manage all those things. There is another model for storage, and which is basically what is called consistent hashing. What we do in this thing is that we try to avoid having a master in the picture. You want to directly use the name and hash it, and then from there figure out where to get the data. So you want to avoid having somebody like a master in the picture. Okay. And this also is used in some other systems. For example, if you look at a parallel file system called GPFS, which IBM designed some time back, they also use something similar to this. Okay. So basically the idea is to, in a parallel file system, it turns out that if you want to parallelize all the activities, you have to parallelize also the lookup part of it also. The path name can be quite long. If it becomes sequential, then your throughput also can be, again, going by Amdahl's law and other things of that kind. The minute your path name lookup is serialized, then the chances of your being able to scale is also that much smaller. Okay. So they had to incorporate abilities by which you can do name lookup in as much as possible without any sequentiality. and the way to do it is by hashing again. Okay. Similarly, there is another file system called Ceph, which also does something similar. It may not use consistent hashing, but it also uses some hashing to take a name and map it to a hash value, and that hash value is used as a way to look it up. Here, what happens here is you are looking for highly scalable storage. So basically, what is going on is people are adding more and more storage, and sometimes some storage also is deleted because of failures. So you want a way in which you can add the storage without having to move things for load balancing. Notice that in the case of GFS and other kinds of models, there is an explicit load balancer, okay, which actually has to move things around, okay, which is done in the background, but it is an issue. Okay, it can actually cost you quite a bit of stuff, okay, in terms of time and energy. Okay. So here the idea is to find a way in which you are somewhat resilient to additions and deletions. That's the basic idea here. Okay. So here the basic model is the following. Okay. You have various objects in the system and you have various devices storing objects. You basically hash both objects and devices using the same hash function. Map each object to a point on the edge of a circle. So basically you have some kind of circle on which all these things are residing, and you map it to various points on the circle. You can either call it a point or a specific angle, either one is fine. Okay. So you map these objects the other way, you also map each device to become storage buckets. For example, we talked about S3, which has a notion of something called storage bucket. You map those storage buckets also onto a series of points on the circle. Okay. Now the object is stored by selecting the closest mapped device on the circle. Okay. And therefore, each device contains the resources mapped an angle between it and the next smallest angle. Okay. So you have to search it only those places. Okay. Again, there is going to be the device, there is going to be some data structures kept here so that you can do the lookup. Okay. So the basic intuition behind this kind of model is that if a device is added or removed, only nearby objects remapped, you don't have to move anything else. Okay. So this is the basic insight about using this kind of system, and you try to avoid depending on masters like what was done in the case of GFS. These kind of systems have been used by some major companies. For example, Amazon has used it, as well as Facebook has used it. Both of these parties have used it, and it's also used in Peanuts also uses it. They also say that you can do storage also in this particular model. They give you that option. So again, just to look at it in some detail, what is being done. This hashing technique uses basically what are called distributed hashing tables, DHTs. So it goes as follows. Okay. So basically what we are doing is we are trying to hash the keys to nodes. Okay. So what do we do here? You have a node with ID, let's say IX. It owns all keys Km for which IX is the closest ID, and there is some kind of a nearness measure which gives you that information. Okay. So for example, you have a key Km, right, and then you can see how close is it to a particular node with ID IX. Okay. So what you do is basically hash both of them, and then you can, from there you can figure out which is the one which is closest, which you have to search. Okay. You can get and that closeness is going to be given by some measure. Okay. For example, if you want to store a file with file name fn, okay, and data in a DHT, you first hash the file name using some hashing function. The one people often use is SHA-1 because it has got very good what is called collision resistant properties. Okay. So these are cryptographic hashing functions which have good collision resistance. That means that even if one small bit is changed, it actually maps to something quite different. Okay. They use some techniques called confusion and forgotten what is that thing called. Okay. They use some avalanche techniques by which this happens. Okay. So you want to store it, you basically get the hash and you say put k comma data, you send to any node in the DHT. You can send it anywhere. And then that node, in turn what it does is, it forwards it from to any other, some other node through some overlay network which connects the nodes, and until it reaches a single node responsible for key k as specified by the key space partitioning. Okay. So essentially things are forwarded till it gets to the right place. So that's where it is stored, and then if you want to get it, you basically send this get, again take the file name and then compute the key and ask for it to get it, and any node can be given to any node, and then it is actually again forwarded, and then it is picked up from wherever it is, and then it is come through the overlay network and it comes back to the client. Okay. So this is roughly the model of distributed hash tables, and as I mentioned, this is what is used by some of these major companies, okay, for storing large amounts of data, so that you don't have to keep on moving things around when some things are getting deleted or added. Here also there are some hotspots and other kinds of things, but we will not discuss it here. Okay. So I just briefly mentioned one example of another system which uses DHT. Basically, it's similar to Big Table, except that they use these DHT kind of models. So it's also a distributed multidimensional map indexed by key, and similar to those kind of other models, the key is basically a byte string, and the value is a highly structured object, just like Big Table. Big Table also has got columns, etc. So same thing here also. And just like Big Table, they also guarantee that any operation on a single row key, right, is atomic per replica, no matter how many columns are being read or written. So they guarantee that particular aspect. Okay. And they also are similar to Big Table in terms of column families, etc. Okay. So the data partitioned across cluster using consistent hashing, and they have a small little tweak. They use some what is called order preserving hash function. So the API is quite simple. Again, we are not going to too much into detail. As I mentioned, there are a lot of there is considerable amount of literature available on each of these systems. Basically, they have three simple methods: inserting, in change. Row mutation is a change into a particular row and a particular table with a particular key. Okay. You can get given a key on a particular table, you can get a particular column, and you can also delete some things, because they have only three methods by which you can interact with the system. Okay. So I'm not going to too much detail about some of these things. Okay. I'm going to stop with respect to details of this kind. So let's just briefly look at what we have seen so far. We looked at GFS, we briefly looked at Yahoo's Peanuts. We also looked at Windows very briefly, Windows Azure, and then we again very briefly looked at Cassandra. So basically, the consensus you can have when you look at all the systems is that they are trying to provide a model of consistency which is manageable with respect to the kind of throughput and let us say the kind of transactions per second you need to support in the system, okay. The kind of operations you need to support, high rates of operations. So I think we can quickly look at summarize some other kinds of models. Basically, you can have either server side consistency models or what are called client side consistency models. That is what for example, the client side consistency models are those what the client sees, and the server side is basically if it has got any replicas, how does it ensure that anything is updated, how does it manage it. Okay. One is coming from what the server has to do, the other thing is what the client finally sees. Okay. For example, if it is server side, we will in summary what we can see what is going to happen is the following. Okay. Let us say that there are n is the number of nodes that store replicas of data. Okay. W is the number of replicas that need to acknowledge the receipt of updates before update completes. For example, if there are 5 replicas, do you wait for all the acts from 5 replicas before you say that the write is finished, or you are willing to take only 3 writes as being completed before you say that write is complete. So W is basically the number of replicas that need to act receive before you say that write is complete. And R is the number of replicas that are contacted when a data object is accessed to the read off. Because in these kind of systems, some of these replicas may not be current. So it might be your bad luck that whatever you contacted may be out of date. So you can control that by having R also. Okay. For example, if n is the number of rows that store replicas, then if you set R equal to n, that means you have to contact all of them. And then you can see easily the fact that some things are out of, let us say, they are not current compared to other ones. Okay. Then you can decide what to do. Okay. Whereas if R is 1 for example or very small, then you can with high chance that you will see some stale version. Okay. So you can basically what is going to happen is that if n is the number of replicas, if you might call W the write quorum and R could be what is called the read quorum. If the write quorum and the read quorum together is greater than n, that means that there is some overlapping thing between the write set and the read set. Okay. And because of this, you can guarantee strong consistency. Again, this is the same trick what Paxos does. They ensure that there is always somebody between two, let's say ballots. Okay. There has to be some guy who is the common between two ballots. That's how they are able to say that if something has been committed in one ballot and it has not been known to everybody still, right? Then other party there will be a way in which information flows from one of the guys in the previous balloting where the thing got committed, it becomes available to the next ballot, like if it gets started. And therefore, whatever decision that was committed becomes known to the second balloting also. And the same thing will be followed. That's why you get strong consistency there. Here also the same story. If you have W plus R less than or equal to n, then it is weak or eventual consistency. I think it should be less than n. It can't be less than or equal to n. Is it less than or equal to? Okay, it has to be less than. This is correct. Sorry, it has to be less than equal. It can be disjoint. Okay, then there is no question. Okay, this is correct. W plus R less than or equal to n. Okay, so then in this case, what can happen is that there could be a disjoint set of replicas, and therefore they might have different versions, and there can be some stale values that could be returned. Now finally, if you think a bit more closely, if r equal to 1 and w equal to n, what is this saying? You are saying that I don't mind reading only one thing, okay, but I am going to make sure that w equal to n. That means that everybody has to be written, every replica has to be written before it is declared as a success, right, and therefore it will be slow, but reads will be fast because you don't have to contact multiple reads, okay. Whereas if w equal to 1 and r equal to n, then you are basically saying that the readers take the trouble of figuring out, contacting all the replicas and deciding what to do with it. If they are out of whack, they might have to do some protocol by which they synchronize them, etc., or make them consistent, okay, whatever. Okay. So typically in web kind of applications, this is what is the typical situation. That's the reason why you will notice that in the case of GFS, there is anytime anything is written, you have to get acts from all the secondaries, right? Then only the master proceeds, otherwise it doesn't proceed. Okay. So this is what most of the large scale web kind of systems will follow, and this is not very common. Okay. I am not aware of any major application that requires very fast writes, and readers are going to be penalized so that the writes can be very fast. Okay. At least on web scale systems, you don't find this much. Okay, that is the server side. Okay. On the client side, I think we already, I am again summarizing what all we have done so far. If it is strong after an update completes, any subsequent request will return updated value. Okay. In a weak case, may return a stale value, right. The special case, eventual model, storage system guarantees that if no new updates made to the object, eventually all accesses will return last updated value. A class example is DNS, which has certain information about the mappings. It will eventually converge to the right values, but there might be some intermediate times when it doesn't converge. It can give you wrong information. The various variations we looked at: causal consistency, similar to when we were discussing group communication systems, we talked about consistent causal models. The same thing out here. That means that if there is a causal reason why certain updates have to have happened before some other update, you need to honor it. Okay. For example, you may have some information kept in some tables, and you might have a requirement that it should not be seen by some people once I make certain kinds of updates. Then it should be the case that if I updated it, then the removing the permissions for somebody to look at it should have happened before the new updates. Okay, that is I want that guaranteed to be given. If that is not given, then I may not be able to, I will not trust the system. Okay. So in some cases, causal consistency is required. Read your writes consistency basically means you can cache your stuff. You can keep updating your own copy, and then anytime you read, you get back your copy. Okay. Whatever you write, but it's not synchronized with the rest of it. Okay. This also in architecture world called processor consistency. Okay. Basically, in a processor, you have something called write buffer. You keep on writing to it. Whenever you read it, it actually looks at the write buffer and gives you the most recent version. But it may not be consistent with other parties who have cached it. They are also writing there. Other model is session consistency. Basically, this is closer to what many file systems provide. What you are doing is you open a session, and then till the close, you are guaranteed that the reads and writes happen the way you expect, and only when the session is completed do you, when you explicitly say close the session, then your updates are uploaded to rest of everybody else sees it. There's also some other slightly simpler models, monotonic read consistency and monotonic write consistency. Okay. In monotonic read consistency, basically if you read it multiple times, they're all in a sense they are consistent. Basically what it means is that I read something, if I get 5, if I read it again, I cannot get 6 if there is no other intervening write, for example. And this can happen, this may be violated in internet kind of scale systems. For example, you read a score of a cricket match, once it says it is some number 320, next time you read it can become 350. Okay. So that's because you are getting updates from multiple different paths, and that will not have monotonic read consistency. Okay. There's also monotonic write consistency. So basically what it means is that if you write something, A for example, and you write B later, then the value of A is seen by everybody before you see the value of B by anybody. Okay. In a sense, you are essentially ensuring that there's some kind of barrier between each write. You first read A first completely, then only you write B. Okay. Again, if a client connects only to a single server, then certain things are trivial. For example, this reads your writes consistency or monotonic write consistency becomes very simple. Again, I just want to conclude with a slightly different kind of model. We are looking at consistency management as a critical one. There are other kind of solutions where a slightly different set of things are optimized on when you're thinking about scalability. Facebook has a photo storage system, they call it Haystack, and for some time they are using NFS, but they found that to read a single photo it was requiring too many excessive disk operations. Basically you need 1 plus disk operation to translate file name to an inode number, because finally NFS uses a backend file system somewhere, right. So it requires 1 plus disk operation to translate file name to an inode number. You have to read the inode number and then read the file. Basically this is required to look up the directory. Then after directory you have to look up the inode and then you have to look up the file. Okay. So there are 3 things required. Okay. So the basic idea here is to see if you can avoid multiple disk accesses. One example of it is to somehow reduce the amount of metadata. Okay. Reduce the metadata, then it turns out that all metadata can be kept in main memory itself. You don't have to go to disk at all. So basically here the problem was that you are going to look up the metadata from disk. So just like GFS also did, but with a completely different, with a completely redesigned file system. What we are talking about here is they are using mostly a similar kind of file system, not too dramatically different, but you want to remove certain things that are not useful. Okay. For example, it turns out in their system, you don't need RWX kind of permissions. It's not needed because there is no, it's not a shared system that they are providing to users. They are just providing photo service. It's at application level. Okay. There is no other user other than this particular photo service that Facebook is providing. So you don't need this permission information. Okay. So you remove this kind of things, then it turns out that typical inodes are 128 to 256 bytes to 512 bytes. This size is too big. You reduce all those unnecessary things, it turns out your inode size becomes smaller, sufficiently small that the metadata for keeping billions of photos is now possible to be kept in memory itself. I think GFS tried to do it by making very big chunks, 64 megabyte chunks. So that's why they reduce the amount of metadata required for keeping them. Here what they are doing is, instead of going for very big chunks, we reduce the size of the metadata itself. Okay. And if you do that, if you carefully look at your system and see what the design, what you are using that system for, then you can essentially eliminate lots of unnecessary things. Okay. And they say that by looking at all this kind of stuff, the high throughput and low latency and at most one disk operation per read. Again, basically you need to scale, and the way to scale it is by keeping all metadata in memory. You can't keep all metadata in memory if inode is very big. So the way to do it is to figure out how to look at your application, see what is really critical information, throw out all the useless stuff, and then you can be able to put it in memory. Okay. The question for us is, why does caching not work? Typically, often they say that if you want one disk operation per read, people often say caching will work. Of course, as we notice, one issue is that inode size becomes too big. There's another major reason why it actually doesn't work also, and that reason is because of, it turns out that Facebook etc. use something called content distribution networks, and these are used for serving hot photos, recently uploaded and popular. Basically, there are systems like Akamai which are used by companies like Facebook to distribute their content so that users geographically distributed can look at the most closest server to pick up that photos, for example. But the problem with these networking sites, social networking sites, is that it seems that they also see a large number of requests for less popular and often older content. This is basically what is called the long tail of the requests. Okay. There are unpopular things, but they are often used now and then. Okay. It seems that these requests account for a significant amount of Facebook traffic, and this will miss in the CDN. And basically, by reducing the amount of metadata, they can essentially get most of the lookups quite fast, and that's what is being served by Facebook. The rest of this being handled through content distribution networks. They basically say that they can do quite well. Because of this, they are able to do 4 times the reads per second than an equivalent system on a NAS, for example. Okay. So basically, I just want to summarize what all we looked at with respect to scalability. So essentially, scalability is a critical issue for web scale kind of systems. You really have to systematically look into cross-layer designs. These cross-layer designs are complicated, basically because instead of the time-tested layering principles, you are going to throw them away and do something new. And typically that means that it requires a lot more careful attention to details. And that's one part of the thing. We saw it how consistency has been taken as one area to do cross-layer optimizations. The other thing that we looked at also was to take care of inode, how to design inodes again. Other issue is handling failures, very important, and because distribution of data is a necessity, and you also have to coordinate updates, that also is critical.